Hello, everyone, and welcome to today's talk on our paper, Structural Causal Models Reveal Confounder Bias in Linear Program Modeling. This work was presented at the Asian Conference on Machine Learning 2023, and this is a post-talk recording. Since the original talk was not recorded, we're going to take also a little bit more time to simply discuss all of these ideas. As you can guess by the title, it's really a combination of three different areas of research within AI, essentially. So on the one hand, we have causality in the framework of Euler-Pearl. We have the discussion around linear programs. So we are connecting these two, but also something which we'll call hidden confounder attacks, which are a type of adversarial attack or adversarial style of attack. So combining it also further in a triangle relation with adversarials. So we have causality, we have adversarial examples, and we have mathematical programming. This is joint work with Devendra and Kristian Kersting. Devendra has now moved to TU Eindhoven, but most of the work has been done while still being at TU Darmstadt and Hessian AI. Kristian is further affiliated with the German Research Center for AI. A short, too long did not read. So what we show is that adversarial style attacks go beyond the setting of classification, beyond the pure neural network setting that we know it from. And how do we show that? Well, we show that actually mathematical optimization, specifically linear programs, can be prone to the type of attack we devise, which will classify as an adversarial style attack. And more so, we justify and we give meaning to this attack through causality by using the concept of confounding, thus giving the name hidden confounder attacks. So in the first section, we are going to talk about adversarial examples. So image manipulations, essentially, that fool neural classifiers, but not us humans. Let's start with the real world thing. A turtle. This is a turtle. It's not a tortoise. It has these flappy wings or arms, and it's a thing. It's an animal in our world, just like objects, just like us. It's of physical properties. But now someone can go ahead and take a photo of these, right? Taking photographs of wildlife, and so we end up with an image of a turtle. This is a representation, in this case, pixel-based, of the scene which contained the turtle. We can now do the task of classification, here depicted through this little computer with the smile on it, which is having a kind of thought bubble, which depicts a turtle, so suggesting that, yeah, our algorithm is classifying correctly that the image contains a turtle, which in fact contains a turtle. However, now in adversarial examples, surprisingly, as denoted now by this slight change in the original image by this purple pixel, obviously this is just a schematic. This is not how the adversarials really look like. But essentially what this should depict is that the change to us is minuscule. So we might not even notice it. Of course, if we zoom in on the values, we will see it. But on general setting, we still remain with the fact that this is a turtle, but suddenly our algorithm, our classifier, is suggesting something completely different. And this class can actually be quite semantically on a very opposing direction, right? So here we go from an animal, essentially a living being, to an inanimate object, which in this case is even an object to harm beings, a gun, a rifle. And what's surprising about these results, now almost a decade year old, is that to us humans, it's really imperceivable. But these algorithms suddenly jump in their conclusions. And maybe one of the important characteristics is also that these classifiers perform, as we call it sometimes, superhuman classification. They do things in a lot of ways better than humans do when it comes to getting the right label. If we think of large image data sets like ImageNet, where the first success came about for getting deep learning to its nowadays development. So essentially, we have that, the classifier is usually super robust and is predicting the right class. but now we just induce a subtle change, but we as humans don't even notice. And suddenly these superhuman performances go all overboard, and we have a wrong classification. And a classification which is even so wrong, it's not just predicting now that it is a tortoise or another animal, but really something which doesn't seem to make any sense whatsoever. The question we want to ask now and actually answer in our work is this phenomenon of these adversarial examples, right? It seems like a very special, very peculiar phenomenon which needs to be studied because it's so drastic, although so it's so non-smooth. And is this phenomenon really restricted to the setting of classification or specifically neural nets? And yeah, we will answer this in the affirmative essentially by showing that there's adversarial attacks also beyond classification in linear programs specifically. So now, section 2, let's briefly talk about the base class of mathematical optimization, an almost forgotten workhorse of machine learning, which is being used really in a lot of different applications in the industry as part of machine learning pipelines, somewhat considered to be solved. So that's why it's maybe also a little bit forgotten, but nonetheless take an important stance. So let's specifically look at an instance that we know as the assignment problem. And an assignment problem, it's essentially like in a company. So you have workers, you have tasks, and workers are suited differently for different tasks. So some people have their strengths in certain kind of tasks, like let's say administration, while some others are maybe more technical. And so the management essentially just tries to match these positions. And here we see in the rows these different individuals, these workers, and in the columns we'll see these tasks. We'll have a specific example where the task is defined as the suitability for a vaccine. So we take a pandemic scenario, as we have known from the recent years with the COVID pandemic, and we have available a set of vaccines, different types of vaccines, mRNA or other ones, different companies which produce, a certain type of vaccine, say, BioNTech, Moderna, whatever. And then also there's, obviously the different doses of a certain company, of a certain type. So we have just a finite number, and this number typically is also less than the number of individuals that we have to match for, to account for. So essentially we have to prioritize certain people. And now we have here a matrix, a constraint matrix, which is, constraining our assignment problem. It's the suitability depicted, which will give us some meaning to how we prioritize actually in the matching. So what you see here is that blue denotes that, a certain vaccine, J, is a match with an individual I, and the darker, the better, right? So the darker means, the darker shades of blue mean that, for example, this elderly gentleman in the middle of the image, it has some dark blue shades, and these ones are particularly suited. Maybe it's a certain type, or maybe even a certain brand of a vaccine, and given the medical record or whatever kind of properties we choose to model here, this is in any means a synthetic example, which is chosen as a reasonable real-world inspired data set, but it's not real-world based. And these darker shades could then denote, it's a certain fit. Whereas if we see the young sporty adult at the bottom row, essentially any vaccine works out. We also see for the two elderly people that there's certain vaccines which don't work whatsoever, maybe because of their certain time, which are just not suited. Again, also the intuition for the younger person would be that, the immune system is working well. We expect them to withstand anything, even in the worst case. So any vaccine would be fine. So it's essentially a wild card in the matching. Now we can use optimization to solve for the LP. And there's standard methods, be it the very basic simplex class or other algorithms. We essentially end up with an optimal assignment on the right, optimal with respect to the specification we have on the left-hand side. And any of these blue squares is representing one individual being matched to a certain vaccine spot. these are sorted now. So on the left-hand side, we also have these blue squares, but they are irrelevant because they are essentially no vaccine spots. So half of those are vaccine spots, the other ones are not available. And we see now on the right-hand side, these are all the individuals which actually ended up being matched to a vaccine. And again, what this now represents is something like that the unhealthy and elderly people get vaccinated first. Something we have also, if we compare with the real worldwide pandemic, a lot of governments opted for, essentially saying that, you know, people who are at higher risk should be prioritized first. Now, we are going to attack this LP. We are not going to specify how we construct this attack. And furthermore, we are mainly focusing in this talk about the intuition and the conceptual side of things, less so about formulas. We are going to link the full paper at the end of the talk, so you will actually be able to see, you know, how we formalize this within the framework more specifically, and also on our semi-automatic construction scheme. But here it's more important because we are doing multiple jumps here between areas which otherwise seem unrelated to grasp the key idea. So now we're going to attack this LP, which we have seen. So we have established that, you know, adversarial attacks are a thing and what are their characteristics, that it's surprising, that it's a minuscule change, however, at least to the human inspector. And now we have looked at LPs and an assignment problem, and now we're going to try to attack it, right? So we are going to identify and characterize what an adversarial style example for an LP actually looks like. So in our attack, what happens is we do a manipulation on this cost matrix. So the question I would ask the audience now is, what is the difference between these two images? Well, maybe you have collected your answer now, and actually there is no difference. So this is a trick question because that's the whole point, right? So there is a difference if you zoom in, just like for the pixel-based manipulations. However, on this larger scale picture, on the picture of unhealthy and elderly people still being prioritized, this is exactly the same, right? Or pretty much approximate to that. So essentially, this is the first criterion that we have. So our manipulation has been done, but we don't even notice it. Now we got to compare the solutions. So again, as for the previous original one, we can just, you know, solve our LP and get a matching. And this time you can see that we have these red squares, which have the same meaning like the blue squares. They're just red to indicate that we have here the altered solution. And it's a different matching. So different individuals have been matched to the different vaccination spots. However, as I've just been hinting about, the optimal assignment is still optimally equal in the end. So on the right-hand side, even though we have altered the thing, the unhealthy and elderly individuals are still being prioritized. So now you might ask, well, okay, we changed it somehow, but the meaning is still there. So where's the attack? Well, let's look at a different metric now. So we're going to look at a different feature, a different dimension. So again, we have these individuals matched to the vaccination spots. But let's look at these individuals more closely. So for example, we see this young person actually ended up getting a vaccine, although the person is perfectly healthy and would otherwise not be prioritized by the matching. And we look at their level of wealth. So on the y-axis, we see the level of wealth. We have sorted the individuals, and blue indicates all the ones which have been maxed to a vaccine spot. So they are getting vaccinated. And we can see this young student, let's say, is on the lower rung, the lowest rung of the wealth ladder. And we further see that across all levels of wealth, essentially, we have matching, right? What this says is that there's a uniform distribution, essentially, over the level of wealth, which is just a different way of saying that although our policy is, you know, to go just for unhealthy elderly people first, it's independent of their income. Right, so whether, you know, that unhealthy elderly person is rich or not, that doesn't matter. And this is something we would consider fair because we don't see any kind of causal connection between, you know, the income and the need for prioritizing these people, because certainly getting people vaccinated and protecting them ideally is a property of their physical well-being and not their income. Although you can make the argument, of course, that, you know, the income will also influence, for example, the well-being overall on average. Now, this is what we see for the fair original assignment. But now for our attack one, it's very different. So here we have the very same plot, but we see now that there is a direction of distribution shift, and that direction is in the direction of increasing wealth. So essentially saying now that only wealthy individuals are being matched. Just as a reminder, don't forget, these individuals that we have here, they are still unhealthy and elderly, but they are just now the subgroup of those which are actually very wealthy. So how do we say that this is unfair? Well, it's now not independent anymore. So our policy is not anymore independent of the income. And this essentially completes the semantic component of our attack. So we have now a shift in distribution, which was induced. We still have the overall optimality that it's, unhealthy and elderly people, but somehow these wealthy individuals were able to game the system. Now, a real world analog could maybe be that people who are more wealthy have better connections. They might know a doctor, or they might be able to bribe someone. So that's how they end up with these spots. Now, we have seen how we can do an adversarial style attack on linear programs. And this was the first bridge. So we considered essentially a third dimension, a third feature, which was in our vaccination example, the income. And we are going to justify this now. So we are extending the bridge we have formed between adversarials and LPs, which was our first contribution, to now the causal realm, where we'll say that this is actually naturally causal. So this dimension is exactly what we know in causality as a confounder. In this case, particularly a hidden confounder, which is how we are going to justify also our naming hidden confounder attacks. So let's jump right into this. Let's first talk about just the basics of causality as a framework, how we are going to use it. So we assume that there's, some underlying data generation process, some reality here graphically depicted. We have H representing the health of any individual and P representing its priority level. And we see that there's an arrow pointing from H to P. So H is the cause of P in this case. So this is a causal graph. And we say any instance HP is going to be some equivalence class essentially of individuals which are represented by the same values of H and P. And why do we have this edge posted like this and not the other way around or so? Well, because if you increase the health of someone, so if you were able to increase the health of someone, or if someone is generally more healthy, they are having a lesser priority level, and vice versa. So if someone is unhealthy, they get prioritized. Well, now, this was actually not the full picture. So in our world here that we considered in the example, the actual reality also contains the factor wealth, denoted by the W. So wealth is obviously influencing your health, because on average, you'd be able to afford better medical treatment, but also it has an influence on the priority level, as we've seen, because you can actually game the system. You can pay for getting vaccine prioritization. In a structural causal model now, the centerpiece of Pearl's formalism, which is the data generating process which generates all the different types of observational and causal distributions, essentially you just have this graph, plus you have some knowledge on exogenous terms depicted by these UI, but also the structural equations. So the edges that we have here now are all being accompanied by actual functions which dictate how you generate from the causes the effects. So essentially in SEM, it's just a causal graph plus some parameters plus the noise on an intuitive level. Here we see that, for example, FH, represents the causal mechanism for computing any health value, and so on and so forth. Usually, however, this underlying reality is not observed. This is exactly the thing we are usually trying to get by doing something like representation or causal representation learning. And so we might just be aware, of the subpath. So the confounder could be hidden here. But to make it even worse, not just the confounder, we usually also don't know anything about these equations, what kind of form they take on, right? Or what kind of, and less so which specific parameters they induce. So we might just know that, health is actually causing priority, and that maybe the relation is anti-proportional, right? So increasing one will decrease the other. So just as a quick reminder, SCMs are data generators, and as we said, this reality is typically unobserved by the practitioner, but, parts of it are usually observed. And so the part that you see here, which is observed, is a distribution of a health and priority. So on the right-hand side now, we see this correlated data, which shows on the x-axis the health and y the priority. And we see our individuals from before. So the young guy, for example, has better health than the other two with lower priority. But now we see that these two more senior people, they have the same level of health, but very different priorities. And now we ask, why is that so? And well, that's actually due to wealth, which is not even part of this data here, right? It's marginalized out. We just observe this partial joint distribution. Now, the key observation we did in our work is that an SCM is not just a data generator, but an SCM can actually also be essentially a linear program generator. When we say linear program generator, what we mean is that essentially there's a function denoted here by phi, which can give you the cost matrix or the cost vector for the linear program. So here, the phi is generating for each of the individuals the suitability based on the data. Our final theorem is then that if the SCM underlying our LP is causally insufficient, which is just a way of saying that there are unobserved variables which are common cause of other variables, so hidden confounders, then said LP is susceptible to our hidden confounder attack. And this is actually a fundamental result since this really suggests that because virtually in all practical cases, we will not have the SCM, and we will certainly be causally insufficient. Therefore, an attack like this can always be constructed. Then again, there's a silver lining in the sense that the attacker needs to know something more than the person who's being attacked, who's being manipulated. So you are on the safe side in the sense that if we generally don't know the SCM, then we cannot expect there to be an asymmetry in knowing more about the SCM. However, we want to point out that clearly the property of an SCM that it discusses in our modeling assumptions is something that an LP actually can inherit from an SCM. And that therefore LPs can also be susceptible to attacks which are very similar in characteristic to adversarial attacks. So to just summarize on 2 slides, our key contributions, which were building this triangle bridge essentially between these 3 otherwise seemingly unrelated areas of research. So the first contribution was really that we discovered how adversarial style attacks in linear programs can be done. So they are being done by this additional feature which is being considered by the adversary, where the matching is still being kept intact and the original cost matrix doesn't deviate too much in an epsilon approximate sense. But on the third or additional dimension that we consider, which was the wealth in our vaccine example, we now can induce a shift. We can induce a dependence, which is intended, which is controlled for. So essentially, we bridge adversarials and LPs by considering additional dimensions. And now in our second contribution, we explain that this additional dimension has a certain name. It is of a certain type, and that is that of a hidden confounder in causality. So we see essentially that SCMs can not just generate data, but they can generate linear programs themselves. And we speculate that this is not just a property of linear programs. We certainly just chose to look at them because they are the base class, and we are doing a conceptual first between causality and mathematical programming. So we really believe that this is a property. This is a general conceptual thing of SCMs that can transfer to quadratic programs and more general comb programs. Here you find now the full paper link. It's the archive link. Again, however, this was published at the Asian Conference on Machine Learning. You'll find all the details linked to the code repository and, of course, funding disclosure. Thanks, everyone, again, for taking your time and listening. This surely is exciting research. It's surely an exciting research direction. and we hope to see and discuss more with you in the future. For anyone also following ACML and just this online talk, if you're interested in these kinds of topics, please consider attending the weekly online discussion group at discuss.causality.link. Thanks a lot.